down rabbit holes. So this is what I'd like to talk about tonight. What I'm going to do is kind of start at the center of the sun where photons are created and kind of go on their journey until they hit the Earth and look at all the things that are part of that journey. But first, we're going to talk about general characteristics of the sun. So the sun's about 4.5 billion years old. It's midway through its lifespan. They think that it should probably complete its lifespan in about 6.5 billion years. So we're at least in our current lifetimes, we're not going to have to worry about it. But our sun is destined to become a white dwarf. There are a couple points in this talk where I articulate with the life and death of stars talk that occurred last fall. But our sun does not have enough mass to create a supernova. And also, there's no companion star to create a type 1a supernova. So it will die as a white dwarf, eventually becoming a brown, or eventually becoming a black dwarf. Unless something remarkable happens, like a neutron star comes by. But it's not going to be a supernova, so it will end its life as a white dwarf. It makes a lot of energy. Every second, the sun produces about 118 trillion times as much energy as the US used in 2003, every second. So it's pretty much of an energy powerhouse, as we all know. It's composed of about 92% hydrogen, which is good to get that's its basic fuel, about 7.8% helium. So in its lifetime to date, it's turned the hydrogen that it began with into some helium, and about 0.2% metals. And one caution here for those of us that know the periodic table is that to astronomers, all elements beyond hydrogen and helium are metals. So the remaining 2.2% are elements like lithium, beryllium, boron, which are intermediate products during the fusion process, and then more stable elements like nickel, calcium, sodium, magnesium, and iron. As we know from the lifetime talk, iron is the final stage of massive stars, but our sun is not massive enough to create these heavier elements. The elements that are in the sun exist as plasma, which is a fourth state of matter that doesn't exist naturally on Earth. And it consists of elements stripped of their electrons and those free-flowing electrons. And that's the state of most of the material in the sun. It requires extremely high heat and pressure to create this state of plasma, and only in the sun is it possible, or a star is it possible to get those kinds of pressures and heat. It's often described as an average star within our galaxy, but actually it ranks within the top 10% of all of our galaxy stars. It's a yellow star in the mid portion of the main sequence, and its spectral classification is G2V, which is in the yellow star classifications. Interestingly, though, our sun looks yellow as viewed from Earth, but if we viewed it outside of the Earth's atmosphere from space, it would look white because it does produce light in all of the visible spectrum, as well as above and below the visible spectrum. But because the atmosphere scatters the blue violet rays, the sun appears yellowish to us here looking at it through the atmosphere. It contains more than 99% of all the mass in the solar system. So despite Jupiter's mass and Saturn's mass and the gas giants, the sun still contains the vast majority of the mass in the solar system. Compared to Earth, it's about 300 times the Earth's mass. A million Earths could fit within the sun's volume. And its gravity, if we could stand on the surface, would be 27.9 times that of the Earth. It's 93 million miles from the Earth, or about 150,000 kilometers. And although most people in this talk probably know this, that equals 1 astronomical unit. So sometimes, at least within the solar system, you hear things described as being a certain number of astronomical units from other things or from the sun. And so the astronomical unit is defined by the distance, the average distance of the Earth from the sun, which is about 93,000 miles. And we know that the Earth has an elliptical orbit, so this is an average, not an absolute. Um, Light takes 8 minutes and 20 seconds to get to the Earth once it's released from the sun. Um, and the sun itself, with the solar system, revolves around the galactic center once every 265 million years. So it itself, our solar system itself, is in motion with respect to the galactic core. The sun is arranged in different layers or zones, depending on what you read about. We're going to go through these next. Um, from the absolute core to about the 20% of the sun's radius, abbreviated here as R sub zero, is referred to as the core. And the temperature here is about 15.7 million degrees Kelvin. And this is where hydrogen to helium fusion occurs. And I'm not going to spend a lot of time with this, but this is the main reaction within our sun that turns hydrogen into helium. Because the question I was asking myself here is where did the protons come from in this process? And this is called the proton to proton chain. There's another way of turning hydrogen into helium called the CNO, or carbon nitrogen oxygen cycle, but it requires much more massive stars to use this cycle than our sun is. So this is the main cycle. And if you look at where the photons come from, which are the energy produced by this, there are two lines of reactions here turning two hydrogens into a helium-3, which then becomes a helium-4. And these are photons. These are gamma ray photons that are emitted here. And then these are, oops, I meant to, these are positrons. This is a new, this is a positron, which is an anti-electron. And when this finds an electron, it's antimatter, and it will annihilate with that electron, and that produces two gamma ray particles as well. So each of these reactions, going from two hydrogen becoming half of this helium nucleus, can produce three gamma particles, which are photons, but very, very high energy photons. And these are the only photons produced by this reaction. And these photons become reduced in energy to visible light in outer layers of the sun. The next 20 to 70% of the sun's radius is referred to as the radiative zone, and that carries energy via radiative diffusion. So the photons and other forms of radiation emanate from the core into this layer, and the photons that become in this layer actually get stuck, kind of bouncing around the different nuclei that are in this. So a photon will get absorbed by a nucleus in there, which will later emit it as another photon. But these photons in this layer bang around for 100,000 to 1,000,000 years. And that means that the photons that are exiting from this layer now and arriving on Earth 8 minutes and 20 seconds later were created in the core around the time that Homo sapiens first emerged on Earth. So these are older photons. And while they are doing this in here, each time they get absorbed and re-emitted by an element in this layer, they lose a little bit of energy and become so. By the time they get out of the radiative zone, the photons are more in the visible light range, the infrared range, and the ultraviolet range, although some are still high energy. But this is how the very, very high energy gamma ray photons that are created from nuclear fusion emerge as visible light and either side of visible light photons. The next zone is the convective zone, which occupies the next 70 to 99% of the sun's radius. And this works much like a pot of boiling water. The hot for water, the hot water molecules rise from the base of the pot towards the surface, carrying energy heat with them. And in the same way, plasma acts as the carrier of the energy in here. So there's a um, a zone here where right between the radiative and the convective zone, where the energy is transferred into the plasma, which then rises and conveys that to the subsequent layers or subsequent zones. And it acts like here the simile is hot water molecules. Later on, I use a simile of an analogy of oatmeal. The final 1% of the sun's radius is the point at which the sun becomes opaque. We cannot see directly below this layer. That temperature has dropped by now from the very, very extreme hot heat of the and pressure of the core to around 5,800 degrees Kelvin. And this is considered to be the surface of the sun where photons escape. Sunspots and granules and other structures that we're going to look at in a little bit are in the photosphere in this layer. The next layer is the chromosphere, which is an irregular layer above the photosphere where the temperature increases from 5,800 degrees Kelvin to sometimes as high as 10 million degrees Kelvin and above. And it's not clear why this occurs. The natural thing is to think that as material moves from the core out to the surface and beyond, it should cool. But in fact, there's this huge temperature jump in the upper part of the chromosphere where the temperature increases from around 10,000 degrees Kelvin to a million degrees Kelvin or more. And I'll look at those in a little bit. There are some hypotheses about why that occurs, but right now we would have to say we're not really sure how that happens. But the color of the chromosphere comes from the fact that hydrogen at these temperatures emits light that gives off a reddish color called H alpha emission. And this can be seen in prominences and in the chromosphere during total solar eclipses or through special satellite-based telescopes and gives the chromosphere its name. Otherwise, we can't observe this. But this picture was taken during the 2017 solar eclipse. And here is the chromosphere here. And you can see these spots of reddish color that give the chromosphere its name. And this was during an eclipse. Similar pictures are available of this using some of the satellites now that are observing the solar observers that can put a block here in the center of the sun and look at just its outer layers. This is what happens inside this transition region. So in the photosphere and inner chromosphere, the temperature is around 10 to the fourth, 10,000. But here in the transition region, by the time it gets up to the corona, it's back up to more than 10 million degrees. And it's not clear why this happens. There may be elements in spikes and jets that protrude into the corona from the photosphere that carry heat up directly into the corona, but it's just not certain right now. The corona could be seen as the atmosphere of our sun. It can only be visualized during total solar eclipses and photographic techniques. You saw in the last picture what the chromosphere and corona would look like. And again, it's much hotter than the sun's surface. And they're hypothesizing high velocity jets from the surface that do this, as I mentioned. Prominences, as we'll go into in a little bit, extend through the corona, which may result in some twisting, which ends up producing some of the effects that we experience here on Earth. But again, I'll talk about that. I found in this talk I had to do a lot of TBDing that I have to mention things here that I'll go into later, but I'll try to cover all those as the talk progresses. So here is a picture of the corona without the chromosphere, and you can see here how it extends way beyond the sun's surface. But again, we can't see it unless we use during an eclipse. And this picture was also taken during the 2017 total solar eclipse. Next, the third section, we're going to go into the surface features, which will include prominences, spicules, filaments, plages, and granules, and solar flares as sunspots. So we'll go into all those in this section. Sunspots are actually relatively cool features of the sun. These are some pictures of some sunspots. They only appear dark because they're cooled off by magnetic phenomena, which I'll explain in a little bit. But because they're cooler than the surface, they look darker. But that does not mean by any means that they're cool. And they're very large. So this is the approximate size of the Earth. And these are large sunspots, which are much larger than the Earth's diameter. And so most of them are, and they can be 10 to the 10,000 to 100,000 miles in diameter. And for comparison, the Earth's average diameter is around 8,000 miles. These are magnetic phenomena. We'll talk about them in more detail when we talk about magnetic phenomena on the sun. And they're often formed in pairs that have opposite magnetic polarities. And these become important when we look at prominences and flares. And we'll, again, when we talk about the stages of the solar cycle, we'll see that the sunspots are changed with the degree of the solar cycle. During solar minimums, they tend to be around the equator of the sun, whereas during solar maximum, they tend to be more in the mid-latitudes, like 30 degrees and 40 degrees. But I should mention that the darkest center is called the umbra, and then these filamentous-like areas are called the penumbra. So spicules are one means by which the corona may get superheated. So there are these structures that extend up. Again, for comparison, here's the size of the Earth, and they extend up from the photosphere. Here's the photosphere here, the chromosphere here, and these spicules, and they go from the transition region up into the corona, and they carry heat directly from the photosphere and deeper layers into the transition region and beyond, which may be one of the ways the corona gets so hot compared to the chromosphere and photosphere. They're jets of plasma that protrude way above and then fall back in. I should point out that this picture is actually from the University of this is from the University of Rochester Astro 104 course. Granules are convection cells in the photosphere. And here's what boiling oatmeal becomes relevant as. So what happens is the relatively hot plasma, this is a single convection cell here, and the plasma emanates from deeper layers in the sun up, and then it reaches the surface where it cools off and then sinks down at the periphery. And you can actually see this like boiling oatmeal. And these are relatively short-lived, although there can be large supergranules that can be as large as 18,000 miles in diameter that can last as long as 1 to 2 days, but most granules are relatively short-lived. So here is a video. Whoops, I gotta turn off my pointer to get that going. Oops. And you can see the plasma rising in the center of each of these granules and then subsiding down below. And this actually will have something to do with prominences, as we'll get to. Oops. A YouTube video, obviously. Plages are bright spots in the chromosphere that usually are surrounding sunspots. They have higher temperature and density than the surroundings, and I don't know much more about them than that. Prominences and filaments, we're going to spend some time on. These are loops of plasma that are pulled up by twisted magnetic field lines. And again, we're going to go more into that. And they're actually the same thing. It's just that whether you call them a prominence or a filament depends on whether you see them with a backdrop of the sun or space. So here's a filament. Uh, here's a loop. And here you're seeing it against space, and you can see the bright loop here, which is called a prominence. This would be called a prominence. But if you see it against the backdrop of the sun, it's actually cooler than the surface of the sun, so it appears darker, and it's called a filament. So they're really the same phenomenon. It just depends on how you're viewing them, whether you're viewing them from the top down against the sun or from a tangential perspective, where you can see them against space. Um, the people write about there being several different types of prominences and filaments. One's a quiescent type, which are the graceful loops that remain nearly stable for hours to days. Then there's an eruptive type of prominence that sends matter upward into the corona at very high speeds, and one called the surge type, which may move as fast as 3 million miles per hour and reach as high as 1 million kilometers above the photosphere. And these more energetic latter ones are the ones that give rise to flares and other phenomena that will eventually affect the Earth. Flares are bright bursts of radiation and visible X-ray and ultraviolet that are caused by the release of magnetic energy. They last minutes to hours. Each flare typically releases enough energy to be equivalent to 1 million hydrogen bombs. The largest flare contained enough energy to power the US for 100,000 years. And these are called by short circuiting of prominences. And I'll get into some detail with this. This is called magnetic reconnection. And the radiation escapes from the sun's atmosphere and expands outward into the solar system. So you see here, these are flares that are occurring, and the radiation occurs outward. And there's also here, this is, I think, a coronal mass ejection, but we'll describe that next. But the flares are what you see when you see the reconnection, sort of like short circuiting of a wire, you get a spark. And that's what the flare is. And we'll distinguish flares from coronal mass ejection in just a little bit. They emit enough radiation to the Earth, however, that of themselves, without being associated with a coronal mass ejection, they can cause radio blackouts and lowering of satellite orbits because of atmospheric heating. The larger flares produce enough radiation that the atmosphere of the Earth actually heats and expands and becomes denser, where some of these high Earth satellites are orbiting and could actually affect their orbits. And some of that has been described, and I'll show that. They're often associated with CME. They'll often be the herald of a CME, but the CMEs, as we'll see, take longer to get to Earth. Excuse me, I'm going to grab a drink. They're classified as A through X, and it's a logarithmic classification. So A, B, and C classes rarely do any harm to the Earth or really get as far as the Earth. M is a little more powerful. M class flares have been known to cause brief radio blackouts, but X class flares are the ones that can cause global radio blackouts and radiation storms in the Earth's upper atmosphere. These flares are unlikely to affect astronauts in space in low Earth orbit, but they're a consideration on Moon or Mars missions, where the radiation shielding may not be as good, or the astronauts don't have the protection of the Earth's magnetosphere, which directs a lot of the radiation around the Earth rather than allowing it to penetrate to lower levels in the atmosphere. Coronal mass ejections, or CMEs, are an immense cloud of magnetized particles. They're generated like flares by realignment of magnetic fields, but they're much more powerful. And they're not just radiative energy, they're actual solar material, plasma, that is pushed out of the sun into space. And a lot of people use a cannon analogy to distinguish flares from CMEs. So a flare is like the muzzle flash of a cannon shot. It's light, you see it immediately, but a CME is like the cannonball. It takes a little longer to get to you. Does a lot more damage once it arrives. And these can have huge effects on Earth, as we'll discuss. This is a picture of a coronal mass ejection, and the flare below it. And I've got some video of that to make this clearer to you guys. All right, so here's an example. You can see here, you'll see these connecting right here. These get larger and larger. The connection occurs right here. And then radiation and plasma are ejected outward, and the remnant of plasma falls back towards the sun. But this is a flare here, and then the coronal mass ejection goes outward. This is a picture, I think, from SOHO, which is a kind of satellite that can block out the sun so you can see the surface things. And here's a provenance, a reconnection event, and you can see the coronal mass ejection heading out towards whatever poor planet is in its way. Are you guys seeing the video on this?
Yes.
Yes.
Okay, great, thank you. Coronal holes are dark areas in the corona that are visible in extreme UV light or soft X-ray solar images. They are cooler, less dense regions than the corona. So these are examples of two. So they're huge, and they allow escape of high-speed solar wind streams. So we'll discuss these in greater detail when we talk about aurora and solar wind. But they produce what are called co-rotating interaction regions, which are interactions of high and low speed solar wind. And they can produce aurora type phenomena on Earth. They're one of the 3 causes of aurora on Earth. And if any of you follow spaceweatherlive.com or any of the prediction, the NOAA or NASA prediction centers, there's a huge solar hole right now, coronal hole right now in the sun that's involves actually most of the visible southern hemisphere that we can see. It's just immense. All right, so we're going to talk about magnetic field in the 4th section here. So a dynamo, before we actually get to the sun itself, a dynamo is any machine or mechanism that converts the kinetic energy of motion into electricity. And the electric currents in turn can produce magnetic fields. And the sun's dynamo, the place in the sun where the electric and magnetic fields seem to be created, is felt to be in the convection zone or in the interface between the convection and the radiative zone. It's not really clear. But the moving electrical charges in plasma create the magnetic field, and the magnetic field results in sunspots, prominences, and filaments, flares and CMEs. And here's an example of some of the stuff. So this is a prominence. It's a loop of magnetic energy which carries plasma up out of the sun with us. So we can't actually see the magnetic field itself in visible light, but we can see the plasma carried up by it. And what happens is this moving stream of magnetism blocks the rising plasma and gas in the sun. So what happens is by the time it reaches the surface, the heating, which usually occurs in the surface of the sun by this hot rising gas and granules, is unable to occur, which results in the sunspots. It's a cool on the surface in the photosphere. And you can see how the motion of mass, the motion of the magnetic field, would result in sunspots, paired sunspots of opposite polarity. If you compare the sun to the Earth has a very stable magnetic field, and this is actually because the Earth's crust, the rocky crust, is stable. It doesn't move. So the magnetic field remains very stable, although over time, the poles do shift slowly and have been known over time to reverse, actually. But compared to the sun, the magnetism of the Earth is much more stable. The sun doesn't have a rocky crust. It doesn't have a stable crust. So different areas of the sun rotate at different speeds. So here at the equator, the sun rotates, one complete rotation of material at the equator goes around in about 25 days. Here in the mid-latitude, it goes around in about 26 days. But once you get up to the polar regions, it takes as long as 35 days. And this twisting of this highly magnetized, highly polarized material in the sun causes all of these magnetic phenomena. So here you can see other examples. And what ordinarily are stable magnetic fields, as this twisting occurs, these magnetic fields are pulled out of alignment with each other and end up getting twisted up. So as they twist and as they get more and more twisted, they burst through as these prominences, which are really the twisted magnetic fields, again, suppressing convection, inhibiting heat flow. The core of the sun also rotates quite fast, as much as 4 times as fast as the surface and intermediate layers. But this twisting of the magnetic field of the sun accounts for many of its effects. So here's magnetic reconnection re-examined in terms of this now. So here is the twisted magnetic field. And as this twisting continues to occur, the magnetic field in the center kind of collapses. And I'm going to do this blind, but one person I saw giving a lecture on this used a slinky. Can you guys see the slinky?
Yeah.
Okay, so if you can imagine an upside down loop, as I twist the slinky, keep twisting, you can see it looping, and eventually these two poles are going to touch, and that causes the flare. And this upper part of the slinky, or lower in this demo, is going to fly out as a flare and CME, whereas the lower part will fall back towards the sun. But if you just keep twisting, the prominence occurs quite naturally. So now my slinky becomes my granddaughter's when I'm taking care of her this weekend. So that's what happens. This continues to twist. As it twists, it forms a connection or reconnection here. The lower part falls back and becomes a new reconnected magnetic field lines. The upper part flies away from the sun as a flare of radiation, and if enough material is up here, as a coronal mass ejection. I'm going to show you guys a film here. Got to turn off my.
On August 17th, 2011, the sun emitted a solar flare. Two of NASA's spacecraft, SDO and RESI, witnessed the event. They saw more than just the flare. They captured magnetic reconnection. Magnetic reconnection is when magnetic fields connect and disconnect, explosively transferring energy. Scientists believe magnetic reconnection drives almost every dynamic event on the sun, including solar flares. While we cannot see magnetic field lines, NASA's SDO can observe solar particles that move along them, tracing out giant arcades of magnetic loops on the sun's surface. Watch the magnetic structure in the background. The cusp flattens out on top. We see reconnection occur as an X shape begins to form and then splits, with half the solar material falling down and the other half escaping into space. A flare bursts from the arcade of loops and reconnection propagates further down the arcade. The observation is verified by RESI data. RESI saw pockets of high temperatures above and below the loops. This signature arrangement indicates reconnection. The two data sets provide visual evidence of reconnection producing a solar flare and will help scientists understand the role magnetic reconnection plays in these amazing eruptions.
Here's another video of showing from NASA showing our reconnection phenomenon that I thought was. So hopefully these demonstration videos can give you the idea of what goes on here. It's really impressive. All right, so any questions about that? I can't see the audience. But anybody have any questions to this point? All right, so section 5 is on the sunspot and solar cycles. Galileo actually noted that sunspots varied in position and number over time. And I'm not sure whether it was Galileo, but people have subsequently observed that each cycle takes about 11 years from the minimum number of sunspots to the maximum. Sunspots tend to be located around the equator, although fewer in number during minimums, and the sun's magnetic field lines are more orderly. There are fewer twists and tangles. And then as time and this differential rotation phenomenon continues to occur, maximums occur. And as the maximum approaches, sunspots increase in frequency, migrate away from the equator to mid-latitudes, and the magnetic field lines become increasingly twisted and tangled. As the maximum occurs, the number of flares and CMEs approach, and we're in the midst of a maximum of solar cycle number 25, right, or sunspot cycle number 25 right now. Researchers construct these things called butterfly diagrams, and these are plots of the location and percent of the surface of the sun covered by sunspots over time. So you can see that each of these is a I'm sorry, I didn't turn my laser. Each of these is a cycle, and you can see that during periods of relatively few sunspots. So I'll point out here that black indicates where the surface of the sun has between 0.0 and 0.1% covered by sunspots. Red goes from 0.1 to 1%, and yellow goes from greater than 1%. So you can see in some of these cycles, you can see that quite a large percentage, relatively speaking, of the sun was covered by sunspots, but not during the minimums. Mostly during the minimums, you see black color. And it's a little hard. The graph below this is the average daily sunspot area percent in terms of percent of visible hemisphere, and you can see how these cycles, the percentage can get as high as 0.5%, whereas there's zero, and it's a little hard to correlate these two, so I just drew in some vertical lines. So you can see here during this minimum, you can see that most of the sunspots are around the equator. Whereas here during this maximum, the sunspots, there's more yellow up here, they're more frequent, and they're also located more towards 30° north and 30° south, the mid-latitudes. So that's a butterfly diagram. It's a very common thing to see in articles and everything about this phenomenon. Uh, with every 11-year sunspot cycle, the north and south magnetic poles switch. And this it's not a violent, or I was reading about this some more today. It's not really a violent, sudden phenomenon. And sometimes it's found that the north magnetic pole or the south magnetic pole will arrive at its polar spot before the other pole does. And it can occur over several years. I've seen articles that say that it's happening now and articles that say that it's supposed to happen. It was predicted to have happened last year, actually, but most people, I think, don't think it's happened at this point. But when the polarity does switch, it usually occurs during a maximum. And so we're expecting it to switch before this maximum is over. Now, there's a second cycle called the solar cycle, compared with the sunspot cycle, or a Hale cycle, named for the man who wrote about it. And that's the time taken for poles to switch polarity and then switch back, which is 2 sunspot cycles, or about 22 years. It's confusing because sometimes you see the sunspots, the 11-year sunspot cycle referred to as the solar cycle. But strictly speaking, the solar cycle refers to the 22 years it takes for the poles to switch and then switch back. And the sunspot cycle is a period from maximum to maximum or minimum to minimum. People have attempted to correlate the degree of sunspots with phenomena on Earth. So the most consistently described association was the Little Ice Age, which was associated with something called the Maunder minimum. Maunder was the scientist who wrote about it, which occurred in the late 1600s when sunspots were extremely rare. There were large periods of time when there were none visible at all in the sun. And they thought that this resulted in cooling of the Earth. The Little Ice Age was a period of time when the Earth cooled greatly. But a recent paper in 2017 that I found said that the Maunder minimum was only one of the factors that were occurring at the time of the Little Ice Age. And this article actually concluded that increased volcanic activity around the Earth and volcanic cooling was more of a factor than the sunspot cycle. Next, now we're gonna leave the sun finally, and talk about our photons' journey from the core in space between the Earth. So that's referred to as the solar wind. And the solar wind is a stream of charged particles released from the corona. It consists mostly of electrons, protons, and alpha particles, which are 2 protons and 2 neutrons, which is the same as a helium nucleus. And it does also contain trace amounts of carbon, nitrogen, silicon, sulfur, and iron. The term Richard Carrington first suggested that there was something like this emanating from the sun. And we'll I'm sorry. We'll see Carrington's name come up a little later in the talk. Eugene Parker, some of you may know that there's a Parker solar probe right now named after him. He was the first scientist ever to use the term solar wind. And there's kind of a cool story about this. Parker's initial paper, where he names the solar wind, was rejected by the Astrophysical Journal reviewers in 1958. And the journal editor at the time a guy named Chandrasekhar accepted it despite the rejections. And some of you may know about a phenomenon known as the Chandrasekhar limit, which is how massive um, uh, a uh, a white dwarf can get before it becomes supernova. It's a limiting factor in how big, how massive white dwarfs can get before they go supernova. And Chandrasekhar was the one who named this. And um, earlier in Chandrasekhar's life, when he first published about this, his articles were consistently rejected. No one believed him, even though what he presented was scientifically sound. And it's like he saw that Parker was being subjected to the same kind of conservatism that he experienced and went ahead and accepted the paper anyway because he had decided that the evidence was sound and he was going to publish it anyway. And the way he passed forward um, to Parker what he had experienced and corrected it, which is, I think, a cool story. The solar wind emanates from the sun in a radial pattern. So when something exits from the sun, remember the sun is spinning relatively rapidly. So when a particle is pushed away from the sun, it has velocity in the radial perspective, but also velocity in the angular perspective. So so something emanating from the sun describes what's called an Archimedes spiral. And the solar wind emanates from the sun like this. And if you want to know what this makes it a little clearer here. So this is from a website called mathcurve.com. And you look at the dot here emanating from the center, and it's moving straight out this line. But because this line is also rotating at a constant velocity, it describes this curve. And that curve is very common in nature, and it's described as an Archimedes curve because Archimedes was the first person who described it and captured it mathematically. The sun's estimated to be losing about 1.2 million tons of material every second through the solar wind. So we're all glad that it has a lot of that material. The solar wind, as I mentioned earlier in the talk, has fast and slow components. The fast component, also hotter, emanates from polar regions, and it's been known for a while that it comes through coronal holes. So when you see a lot of coronal holes in the sun, you know that there's a lot of fast component solar wind emanating, and its composition nearly matches the composition of the photosphere. The solar component of the solar wind hasn't been previously associated with coronal holes, and no one really knew what it was comprised, what it was caused by. Its composition is more similar to that of the corona rather than the photosphere. But last week, I got my copy of Sky and Telescope, and on page 10, they had this article titled "Solar Orbit Traces Origin of Solar Wind." And so this article argues that there are picoflare jets within these coronal holes that are the source of a lot of the slow component of the coronal wind. And this is the first article ever to really attempt to link coronal holes with the slow component of the solar wind, which I thought was interesting. I'm glad Sky and Telescope came out last week. And if you look at, I mentioned earlier these things called CIRs, or co-rotating interaction regions. So this is the Archimedes spiral. This is the slow component of the solar wind. This is the high-speed component. And what happens is the high-speed component eventually catches up with the slower component and produces a compression area here where the high-speed component compresses that, and these are called co-rotating interaction regions. And when these affect the Earth, they're shock-like structures that can mimic to a much, much lesser degree CMEs and give rise to aurora phenomenon. So there is another cause for auroras besides the CMEs and the solar flares, the radiation alone. Next, we're going to talk about space weather, which is finally reaching Earth. So just to quickly review, flares are energy released from magnetic field loops through magnetic reconnection. Comparable to the muzzle flash of a cannon shot, they move at the speed of light. So when they occur, their effects on Earth occur 8 minutes and 20 seconds after they occur. CMEs are matter released from magnetic loops and reconnection, more like the cannonball, much more destructive, slower though, and they take 2 to 3 days to reach Earth. So we have very little time, 8 minutes, to react to an X-class flare. But we have 2 to 3 days to react to CMEs. And so that's why websites and NASA projects like space weather prediction exist, because these are much, much more destructive than flares. And if we have 2 to 3 days when we can detect them, the earlier we detect them, the more we can do things to protect ourselves from some of their effects. And things like turning off satellites, protecting astronauts, things like that. So, so the slower but more destructive nature of the CMEs gives rise to all the emphasis right now on space weather prediction. And I already mentioned CIRs. Flares, as I've mentioned, because the Earth is protected by its magnetosphere, have minimal effects at the Earth's surface. But the Earth's upper atmosphere is affected by the high energy photons, including X-rays and some gamma rays caused by these flares. The Earth's outer atmosphere can be heated and expands, and because these lower satellites are now passing through much thicker atmosphere than they were, it can degrade their function and also their position. It can affect the positioning of the satellites. It can also cause direct damage to satellites that are in high geosynchronous orbits. So currents can be induced by the energetic radiation from the flare. And that can cause damage within the satellite, and the energetic particles can also cause direct damage. Geomagnetic storms are the manifestations on the Earth of what goes on in the sun. So they're formally defined as the atmospheric effects on Earth's surface from events that occur on the sun. They're caused by CMEs and to a lesser extent CIRs. Again, geomagnetic storms occur at the Earth's surface, so flares have less things to do with geomagnetic storms. They're on a scale of G1 to G5. I won't read this for you, but G1 is relatively minor with some minor blackouts, some grid disruption. The G5 can be complete blackouts, complete collapse of power grids, navigation systems may be down for hours or days, and auroras can be seen as low as Florida and southern Texas, and we'll see some examples of this in a second. So again, the better we can predict geomagnetic storms, the better off we can do things like that are known to protect some of these things. And in our case, the more quickly we can run out and see the aurora. Historical geomagnetic storms, I told you we're going to see Carrington's name again. This occurred in 1859. It was caused by a CME, the flare of which was directly observed by Carrington as he was observing the sun. It caused extremely bright auroras occurring atypically in the south. These were so bright that it was written that people in the Caribbean were able to read newspapers at night because of how bright the auroras were. And in California, gold miners woke up and made breakfast because they thought it was sunrise. That's how bright it got. The electromagnetic effects of this caused fires in telegraph stations. They ignited telegraph poles. And telegraph operators were reported to be able to operate their telegraphs without connecting to batteries, just using current induced by the storm in the wires. Railroad ties were also ignited by induced current in the railroad rails. This is a big event. Other historical storms, the New York Railroad storm occurred in May of 1921, causing destruction of telegraph and telephone systems, fires in telegraph offices in New York City, a superstorm in 1940 caused by a pair of interacting CMEs, which just occurred to us last week. There were two interacting CME storms that affected Earth last week as a glancing blow. These disrupt power grids and long-distance communication across North America. In 1972, there was a solar storm that disrupted electronics and caused enough damage to AT&T's transatlantic cables that they were forced to redesign its system to protect against solar storms. There was a blackout in Quebec in 1989 that disrupted satellites, caused province-wide blackouts in Quebec. And NASA at the time, it probably still does, has a system for tracking 19,000 Earth orbiting objects. They lost track of 11,000 of these because of the atmospheric effects of these, because their orbits change. Because of the atmospheric effects of the flare and the accompanying CME, these orbiting objects, some of which were natural, some of which were satellites, changed, and NASA lost track of them. If a Carrington event occurred today, this woman who wrote in BBC at Night's Sky at Night magazine, she's a professor in computational space physics at the University of Helsinki, whose life has been spent studying magnetospheric physics and solar wind magnetospheric interactions. So she's a highly qualified academic, and she writes that there would be as much as $2.5 trillion in damage, that there'd be global multi-day, week-long even air traffic restrictions due to high radiation doses at altitude. Mobile phone network could be completely interrupted. Satellites could malfunction, and it could take us months to years to recover from this. It would be catastrophic. And right now, we don't have a lot of ways to protect ourselves. But on a positive note, these events do cause auroras, which are greatly pleasing and nice to look at. Auroras are caused by charged particles from the sun interacting with the Earth's magnetic field. So these are the solar wind, these are charged particles. And if there's a flare or there's a CME, there's more than the usual number of charged particles. These are directed upward and inward by the Earth's magnetosphere. Some of them actually go past and then are redirected back to Earth by the magnetosphere from beyond Earth. But they all come in at the poles. They energize elements in the Earth's atmosphere. So as these photons come in, elements in the atmosphere absorb them. Electrons in the elements move to higher orbits because they've absorbed these high energy photons, and then they fall to lower orbits and re-emit photons, colored, lower energy photons that are colored. And that's how the auroras occur. They're mainly at the upper latitudes because of the phenomena I just mentioned. We're lucky in North America because our north magnetic pole is in Canada. So here's the geographic magnetic pole. And to orient you, here's Alaska, here's Hudson Bay, and then here's a picture of the magnetic North Pole. So here is the geographic North Pole. Here's the magnetic North Pole, which is down in this area. So you can see that this oval extends further south and on the North American continent than it does on the European continent, because it's centered around the magnetic North Pole, not the geographic North Pole. So, I always tell our daughter in Stockholm that we see more aurora than they do for this reason. The colors of the aurora are caused by the specific element that's absorbing and then releasing photons, and it's height above the Earth's atmosphere. So the red color is from atomic oxygen. that is between 150 to 200, that above to 150 miles. Green is caused by atomic oxygen lower than that in the atmosphere, up to 150 miles. The To be visible to the naked eye, the red color emitted by atomic oxygen at this level has to be 10 times brighter than the green counterparts, which is why most of the time when we see aurora, we see these green and maybe bluer colors. The red that we saw, for instance, last October is relatively rare and requires much brighter aurora to see than usual. Violets from ionized molecular nitrogen above 60 miles, and ionized molecular nitrogen below that comes across as blue. So the colors actually indicate which oxygens, which molecules and where are being affected and emitting the light. The stronger the magnetic storm, the more likely the aurora is to appear. So the KP index, which is German, and I'm not going to try to pronounce this, translates loosely to planetary index number. And it's a global geomagnetic activity index that's based on 3-hour measurements from 8 ground-based magnetometers around the world. One of which is in Kiruna, Sweden, which I visited, but before I knew anything about this, but otherwise I might have been able to visit it. It can range from 0 to 9, and any KP index greater than 5 is classified as a geomagnetic storm. So when this coronal mass ejection affected Earth last week, the KP index briefly was as high as 6, but it was, of course, cloudy here, so there was no chance to see any aurora that might have happened. Another measure of value in predicting aurora is called the BZ value. B is a symbol used to reflect magnetic fields, and the solar wind can be represented as 3 different vectors: the BX vector, the BY vector, and the BZ vector. And the BZ vector is oriented through the north and the south poles of Earth. And a positively charged BZ value, the chart of the particle flow is flowing north to south. And in the negative situation, it's flowing south to north. And so when it's flowing south to north, these particles bang directly into the particles that are moving because of the Earth's magnetic field. So it's a much stronger, more energetic interaction. And so highly negative BZ values for any given KP value is much more likely to cause an aurora. So if you want to go to, let's see now, Jackie, I need to stop my sharing so you can go to these websites. All right, so do you guys see the Space Weather Prediction Center?
Yes.
Okay. So I can't see what you're seeing because of the way my screen's set up. But this is I check this every morning when I get up along with the newspaper headlines. And it's much more enjoyable than newspaper headlines. Because I can look at the KP value, I can look at the BZ value, I can look at the auroral ovals, and a space weather, which is the NOAA predictive. I had these bookmarked to show you guys, but for some reason I can't get the website to show on the screen share. But go to these websites and take a look. They've got immense amounts of information, both about the status of the sun. You can see the coronal holes. You can see what the sunspot count is every day. They're just, and each section of these websites has links to learning pages where you can learn more about them. They're really, really spectacular. And I really recommend it. Again, I start my day out with them almost every day. Okay, Jackie, if you want to stop screen sharing, I will start again. Okay. All right, now you should see a slide that says associated phenomena.
Yeah, we're seeing your notes, so you're in presenter mode as
Oh,
opposed
oops,
to.
okay. So let me stop sharing. Sorry, you guys. Is that better?
Bingo.
Okay, great. All right, so a phenomena associated with auroras, there's one called Steve, um, which is called strong thermal emission velocity enhancement, which is a mouthful. And actually, the reason why it's a mouthful is a great story. This was discovered actually by citizen scientists in Canada. It's linked to but distinct in causation from the aurora, thought to be chemiluminescence, hot, heated, glowing neutral gases versus charged particles for the classic aurora. And it turns out that the name Steve comes from an animated film called Over the Hedge. When I read this story, I actually watched the whole film. But in this film, there are animal characters that awaken from hibernation and discover a huge mysterious hedge has been built in their woods. And they decided to name it Steve in an attempt to make it seem less mysterious and less scary. And so these citizen scientists decided they wanted to name this phenomenon that they observed Steve. And they back engineered the acronym Steve to be strong thermal emission velocity. But it really doesn't mean anything except that they wanted it to come out to be Steve because of their love of this film. So an example of this actually comes from um, our own Farish. So we were at Farish on I think it was just a regular public observing night, and we saw this in the sky and didn't know what it was. Um, and almost everybody, certainly myself, because I'd never heard of Steve at this point, thought it was a jet contrail. And people were arguing about whether it was Steve or not. It didn't really look like a jet contrail. It didn't spread out like a jet contrail would. And then a few minutes later, it did this, which a jet contrail would not do. So we think this was Steve, although there are people who to this day disagree with that. But we think we saw an example of it that night. Um, and it's said to be associated with auroras. I'm gonna, next time I go out to see an aurora, it said that it's very frequently in an aurora, but you're so fascinated by the colored aurora that you miss the fact that there's this white line that's also extending across the sky. So something to look for while you're observing an aurora. There's also something called a structured continuum mission, which has only recently been described. It's whiter gray in color. This is the only image I was able to find of it. And it's said to be different from both Steve and the aurora, but I'm not going to go into it very much at this point. So this is a picture I took last October at Webster County Park. But the real great picture I'm going to leave you with is this picture by Joe Altieri, shown with permission. And this is why we look at this stuff, for this experience watching this. I'm going to say thank you for watching this long talk, and I can open it to questions if I can stop sharing. Thoughts, questions?
Thank you, Craig. It was a wonderful talk.
Thank you.
Someone who knows very little, it's a great intro for me. Can I ask a question? It's probably very naive. As we've looked out into our own a galaxy, what is there some idea of what percentage of stars are essentially at the same stage as our sun is at?
Yes. And we're in something called the main sequence, and the majority of stars are actually cooler than us and smaller than us. Red dwarfs and but I can't remember the exact numbers. But ours is ours is not as large as it gets, but it's an above average size star.
And of the stars in the galaxy, is there some estimate of what's the number of stars that are at the same stage as our sun and similar?
I don't know. I should have read that because I probably went over that data in my star talk, but I will get back to you with that number.
Thank you.
And it's just to note, all the stars that we can see are in our galaxy. So we cannot see individual stars in other galaxies at this point.
Right. That's why I was asking about this one.
Yeah, yeah.
Thank you.
Well, great. Well, thank you all very much for hanging in there, watching this talk. I learned a huge amount doing it. I'd like to invite again anyone who is as inexperienced an astronomer as I am to think about giving one of these talks if there's something you want to know more about. I would be willing to work with anybody to put a talk together. Just contact me with whatever your field of interest is in. I'd be happy to help with slides or references or whatever I can do, because I'll learn something as well. But the more inexperienced people we have given these talks, the more the other people are going to learn. So, will be our next talk will be the fourth Wednesday in May, and I believe that will be about how to buy a telescope by somebody from the Mohawk Valley Astronomy Club. That'll be a good one.
Greg, this was awesome talk. Thank you very much.
Well, thank you for attending.
Thanks, Craig.
Awesome.
Great
You're
job,
welcome.
Craig. Thank you.
Thank you.
Thank
Good night,
you, Craig.
everybody.